All right, in this video, I'm going to look at the difference between distance and displacement. We'll talk about what makes each one unique and how to find a value for them given a certain scenario. We start off by saying both of these things measure how far an object moves. What makes them different from one another is their frame of reference or their point of view. In the case of distance, the frame of reference or point of view is the object itself. It's how far the object's moved. It's how far the object has gone. A good example of this is the odometer in a car. The odometer in a car measures the distance that the car has moved. It's all about the car, all about what the car has done. The frame of reference is the object itself. In displacement, the frame of reference is the starting position. No longer do we care about what the object has actually done, but what we're concerned with instead is how far away from the starting position our object has gone. So let's say you're at home and you need to get to the store. There are very few instances in life where you can drive in a straight line to get from one place to the other. You end up going down one road, over another road, down another, kind of snaking whichever way the roads take you to get to your destination, in this case, the store. Your distance is all of that. So if this were 1 mile and that was 3 miles and that was 1 mile, and this was 4 miles, and that was 1 mile, we would add everything up to find out the distance that you traveled. 4, 5, 9, 10 miles. Again, the distance is the total that you traveled. Your displacement, however, would be a straight line distance from where you started to where you ended. And that is almost always shorter than the actual distance itself. We might find that this is only 7 miles. You abbreviated delta x. Displacement is abbreviated delta x, distance is abbreviated d. The distance we travel would be 10 miles, the displacement would be 7. Now, if you've ever noticed, like when you put something in a GPS, and you're searching in a new area to try to find something like a McDonald's, it gives you a whole list of McDonald's that are in the area, and it tells you a number of miles to get to those locations. And then when you select one and tell it to actually route you there, the number of miles don't match. For example, in the list, it might have said it was 4 miles away, but when you actually went to map it, it was 5.8. What you're looking at is the difference between distance and displacement. When you originally search, it just does a straight line distance between you and all the locations. It does the displacement. And then when you actually select one, then it maps you, it takes the roads into consideration and tells you the distance. It's actually two different things. Now, we're really not done with this because the second thing that we need to know about distance and displacement is that distance is a scalar quantity and displacement is a vector quantity. Now, scalar quantities have only magnitude. That is a number and a unit. As we see here, 10 miles. This is the magnitude of my motion. It's the number and the unit. Vector quantities require direction. Vector quantities are magnitude and direction. So we have to come up with some way of describing this motion. And we could say that that is to the east. The difference being our frame of reference. When you're looking at the car, it doesn't really matter what direction the car is facing or where the car is going. All that matters is the car is going. When you change that frame of reference to the starting position, now you have to think a little differently. Now we can say not only how far away from the starting position we are, but we can also say which direction we went. Gives us more detailed information, gives us that extra layer. Again, we need to be able to describe these distances and displacements in a number of different scenarios, using a number of different techniques. One of which is just analyzing straight up word problems. A person walks 3 meters east, then 1 meter west. What is the distance and displacement? This is about as straightforward and simple as a problem like this gets. We can visualize it in our head. We can draw a picture of what's going on, doing something to help us figure this all out. So the person starts here, goes 3 meters to the east is right, and then comes back 1 meter to the west. 3 meters in this direction, and then 1 meter in that direction. The distance is going to be the total motion. And to do that, we just add the two together. 3 and 1 is 4 meters. To find the displacement, what we need to know is the distance from the starting position from here to there. If it went 3 east and 1 west, then stands to reason we are still 2 meters away from our starting position. So we say delta x is 2 meters. And again, that's just the magnitude part of it. We do need a direction to attach to this. So we're using east-west coordinates. We would be east of our starting position. And again, that's about as simple as one of these types of problems get. Taking it to the next level, we start stringing together more components of motion. We start doing more stuff. So instead of just going east and then west, we start making them do all kinds of crazy stuff. 3 meters east and 1 meter west, and 4 meters west. Then 7 meters east, then 2 meters west. What's the distance and displacement? In this one, we have several different components to look at. Now, the way it works for us here is it really doesn't matter what order everything is done in. We can actually group things together, simplify things, and then come up with a simpler problem to look at. The way I would start is by getting together all of my components that are in the same direction. So starting with all the east ones, we go 3 meters east. Thought about it across them out so you don't get them again. The next one is a west, the next one is a west, and then we have a 7 meters east, and then the next one's a west. We have 2 that are in the east direction. We add those up for a total of 10 meters east. So in all, our person has gone 10 meters to the east. Now we do the same thing with all the western components. We have a 1 meter west. We have a 4 meter west. And then we have a 2 meter west. And again, we're going to add all those together. That is a total of 7 meters west. And once we've done that, now we have a relatively simple problem to look at, a simple problem to think about. So a person starts there, goes 10 meters east, and then comes back around 7 meters. So now it just looks like the original simple one that we had up here on the board. Again, the distance is going to be the total, so 10 plus 7. This person has walked a distance of 17 meters. The displacement is going to be the distance from here to there. So if we've gone 7 meters back, that stands to reason we have 3 meters left. And again, we need a direction. We are east of our starting position. So once you've gone through and summarized and taken all of your parts that are in the same direction and simplified them into a single number, then you have something that looks identical to what the first one did. We will often use number lines when we do distances and displacements in linear motion. It saves us from having to write all this east, west, left, right, up, down stuff. And gives a simple picture to work with. Number lines will have a 0 on it somewhere. All the values to the right will be positive numbers. I'm not going to write a unit on this, but wherever you don't see a unit, you can assume it's probably meters. Everything to the left is going to be negative. So all of our numbers to the right of 0 positive, left of 0 is negative. This is no different than it is in any math class. There's a couple of ways I can do this. I can put some letters on here and tell you something like the person goes from A to C, then back to B. What is the distance and displacement? Well, first we got to figure out what happened. So we have to take this part and use the number line to turn it into numbers. So from A to C, and we can just count these out. From A to C is 1, 2, 3, 4, 5, 6, whatever our unit is. And again, if there's no units there, you can say that it's meters. And this motion is to the right. So 6 meters right is our first part. And then it says the person goes back to B. So it goes from C back to B again. That is 1, 2, 3, 4. And this time that would be motion to the left. Now once we've done that, it's exactly the same as what the very first one was. So the person starts here and then turns back. This part is 6, this part is 4. For our distance, it's the total of the two. The person walked 10 meters. And for our displacement, it's from here to here. If we've done 4 meters back, stands to reason we have 2 meters left. So delta x would be 2 meters. Directionally, we want to stick with the things that we were doing here. We were doing left to right. If you were doing east to west on there, you'd use east or west. That would be to the right. Just stay consistent. Don't switch from left to right to east to west when you're doing a problem like this. Now, the second way that we could illustrate or show you this motion is instead of putting letters on the number line, we could draw some arrows. Draw something like this. And ask you for the distance and the displacement. Again, we got to start by going through and figuring out what each part is. So in this first part of the motion, as we're moving over here to the right, this part of the motion is 1, 2, 3, 4, 5 meters. Then the person turned around and went back to the left, starting here, moving back this way, went back 1, 2. So that part is 2 meters. And then from 3 to 4, that is a 1 meter motion. So again, for our distance, we're just going to add all these things up. It was 5 this way, then 2 that way, then 1 that way. We ignore the vertical component because it really isn't 1. Everything is linear here. So 5 plus 2 plus 1, the person walked 8 meters. For our displacement, what we have to look at is how far away from the starting position we are. And basically, we're ending here at 4. We went 1, 2, 3, 4 meters, and we went to the right. So again, just a few examples of how distance and displacement can be done this early stage in the game. The last and final thing kind of takes it to the last level, the highest level from which we're working at this point. And that's when the components of motion really aren't linear. And this really is starting to look forward a little bit into something we're going to call two-dimensional motion. We'll be doing a lot more of this later. Person walks east 5 meters and north 3 meters. What is the distance and displacement? Now, when we draw this out, our person went 5 meters that way and then turned north and went 3 meters. The distance part of this is just the same as it always is. We just add those two things together. The distance is 8 meters. But when we want the displacement, what we're really talking about is from the starting position to where we ended. This is delta x. And the reason I threw this in here now is because this is just basic Algebra 1 stuff. This is material that you've done a few years ago. To find the answer to this, we would use the Pythagorean theorem. A squared plus b squared equals c squared. Doesn't matter which one you make a squared or b squared. So 5 squared plus 3 squared equals c squared, or 25 plus 9, or 24 equals c squared, or 34, not 24. 34 equals c squared. And then we need to grab a calculator. Square root 34. So the square root of 34 is 5.8. So my displacement, 5.8 meters. And again, I threw this in at you now to give you a kind of an idea of how far this is going to go. You should know how to do Pythagorean theorem already, so this really isn't that big of a stretch. We will do a lot more with this when we get to two-dimensional motion because we'll be talking about velocities in different directions. Like if you're trying to swim across a river while the river's trying to pull you downstream, we'll figure out what your velocity would be using this technique. At this point, that's all the further we're going to go with it. Directionally, we're just going to say northeast. When we get to the more complicated unit on this, you'll be calculating this angle, and you'll be using that for your direction.